and pull up the answer key. And that's the wrong chapter. Yeah, I clicked on the wrong button. Let me try again. There. Chapter 3 homework. All right. I do know that there were a few glitches on the weighted average calculation here. Please keep in mind that a weighted average is not done mathematically the same as a traditional mean or average, because it takes into account the percent occurrence or percent abundance of the item that you are looking at. So in this case, I have mythical tomatoes, and I gave you percentages that matched each of the weight brackets. 20% at 155 grams, 38% at 160 grams, 15% at 178, and 27% at 190. So look at the math here in that you must take the mass in grams and then move the decimal place on your percentages. So instead of 20%, you're multiplying by 0.2. Instead of 38%, you're multiplying by 0.38, etc. Multiply across, that gives me my four values, 31, 60.8, 26.7, and 51.3, and then total them. There is no division step in a weighted average. You're not dividing by 4, okay? All of that is taken into account by the fact that you are multiplying by your percentages. So then we move into going back and forth between grams and moles and atoms. I gave you 43 grams of strontium. So a lot of the rest of this chapter involves heavy usage of your data from the periodic table. Take your 43, you are dividing by the atomic mass, and that gives you 0.491 moles. Going in the opposite direction for number 3. I have 0.15 moles, so when I look up fluorine, being 19 on the periodic table, this time I am multiplying rather than dividing, and I get 2.85 grams. If you are calculating atoms, you need to do this in 2 steps. Now, you could have linked the 2 steps together. I did one step, got an answer, then did the second step. Mathematically, it will not give you different answers. Take your 6 grams, divide by the atomic mass of bromine. This will give you 0.075 moles, and then use your Avogadro's number, 6.022 times 10 to the 23rd, to get 4.5 times 10 to the 22nd. If you ended up with an error in your exponent, here is a suspicion you might want to check out. If you are using a calculator, especially if it's a TI calculator, if you use the caret key as the way to indicate what the exponent of 10 is, depending upon if you hit a times 10 in between there and you also hit an exponent key, that is a common calculation error on the calculator. So beware of the order in which you are punching buttons. Then we move on to molar mass. This is a relatively large molecule here. We have 3 tins and 2 phosphorus atoms and 8 oxygens. So again, back to the periodic table to look at what your atomic masses are. Multiply across. That way I get 356 and 61 and 128. And then you can total them all together and you end up with a relatively large molar mass of 546. Continuing onward with the usage of whole molecules now. If I have a quarter of a mole of copper cyanide, first thing I have to do is figure out how much 1 mole weighs. Add up your numbers. Then multiply by your quarter of a mole, and you get 22.39, or if you rounded it, 22.4 grams. Going back in the opposite direction, if I give you 50 grams of potassium acetate, total up your values, 39 and 24, and 3 times 1.008 for your hydrogen, 2 times 16 for your oxygens. Your molar mass is 98 and change. And then you are dividing your 50 grams by your molar mass. You get a little over half a mole. Moving onward to mass percents. Note, one of the reasons that I teach doing the molar mass by a particular method is it streamlines things when you are doing percent by mass and some of the other related calculations. I've got potassium dichromate here. My 2 potassiums, my 2 chromiums, my 7 oxygens. Since I multiplied across, I've already done some of the math I need in order to calculate my percentages. My full molar mass is 294.2, so it goes in the bottom of each of my percentages. Take your 2 potassiums together. For the top of your percent potassium, you get 26.6. Your 2 chromiums together puts 104 on the top of that one. You get 35.3%. And all 7 oxygens together gives me 38% oxygen. Then we switch over to empirical and molecular formula. So I gave you percent as your initial information for cadaverine. I ran across this in another textbook. You first must divide each of your known percentages by your atomic masses from the table. So 12 for carbon, a little over 1 for hydrogen, and 14 for nitrogen. That will give you mole values: 4.87, 13.7, and 1.96. Divide by the smallest one. This does not give you whole numbers. It gives you 2.48, 6.98, and 2. You cannot just round. You must multiply all of those by 2 in order to get rid of the half that occurred with your carbon. This will give you an empirical formula of C5H14N2. If you compare that to the quoted molar mass of 102.2, you will find out that they match within a tenth or so. So my empirical and my molecular are identical. The other one of similar profile here is one that starts out with grams. So I gave you 32.79 of sodium, a little over 13 of aluminum, and a little over 54 of fluorine. Again, look up your numbers from the periodic table. We've got 22.99, 26.98, and 19 for fluorine. When I do my division, I get 1.43, 0.48, and 2.85. Divide by the smallest one, your 0.48. These come out very, very close to whole numbers. So the 2.98, 2.97, you can round up to 3. The aluminum is divided by itself, so that's your 1 that becomes 1. And 5.9 is still pretty close to a whole number, so I can round that one up to 6. There is no need to multiply by 2 to get rid of halves in this particular problem.
Ooh, I have a question.
Yes.
On that one right there, I got it. I kind of figured you didn't want us to do round up. I mean, you didn't want us to multiply to get a whole number, but when will that rule exactly apply? So like, I know 0.5, you will multiply to get a full whole
So
number,
the one
right?
above, the one here that has the 2.48 is almost smack in the middle. So you could assume you need to multiply by 2. Any other problems that I would be likely to give you, especially test-wise, will either be very close to a whole number or pretty much dead in the middle. They're going to be one or the other. I'm not going to give you something that's really kind of gray and you have to make a judgment call. It's got to be one or the other. It's got to be a half, 2.5, 3.5, 4.5, 1.5, in order for you to need to multiply it by 2.
Okay. Thank you.
All right, and then we do a little bit of solutions here. Calcium nitrate. So I need to know how much 1 mole of calcium nitrate weighs. So I added that all up. That gave me 164.1. Multiply your molarity, 0.6 moles, times your quarter of a liter. Make sure you are moving your decimal place because it cannot be left in milliliters. It has to be done in, it has to be converted from milliliters over to liters. That gave me 0.15 moles. And then I used my molar mass. So I would have weighed out 24.615 grams of my calcium nitrate. Going back in the opposite direction, I gave you a gram weight, 35 grams. So you are dividing by your molar mass. That will give you 0.216 moles. And then you are dividing again by milliliters converted over to liters to give you 0.539. You need the M1V1 equals M2V2 equation for the dilution. So your concentrated hydrochloric was 7.5 molar. You want it much less concentrated, 0.115, but you want to make a half a liter of it. So I put in all my numbers. I got an answer in liters, and then I moved my decimal by multiplying by 1,000 to get milliliters. And the most common mistake on the final problem was the fact that when you are doing percent by mass, some people did not add together the 89 grams of the potassium nitrate with the 1,000 grams of water. They have to be combined together when you are doing percent by mass. So if you did not have 1,089 on the bottom, I might have written wrong denominator when I saw those errors. Questions about this homework set? All right. So we are going to dive back into some more of chapter 4. We've done a pretty good chunk of this chapter. I posted a version of it that has a couple of additional figures in it on the the Canvas page because I decided that it would be helpful to have the stoichiometry roadmap for when we get to that. And so let me switch back over to my different file here. All right, we got through looking at a few categories of reactions. So the next big chunk of this is redox, which actually stands for, or is kind of weirdly, a contraction of oxidation reduction, which makes you think that, well, why didn't they call it oxred? Which would kind of make more sense when they quote it that way. But you will find most textbooks call it oxidation reduction, yet they also call it redox. In some ways, it has the most, I'll call it moving parts, in terms of the types of things you have to do to make these reactions work. And it's all about the electrons. They are the currency of this kind of reaction. You are losing and gaining, or transferring in order to make these kind of reactions happen. So, little mnemonic device. There are some other ones, but this is the one that I am most used to seeing, is oil rig. Oxidation is loss, reduction is gain. So little brain trick there, which sounds backwards, because it's like, wait a minute, if I'm gaining, how can it be reduction? The thing that you are trading around is negative. If I give you a bill for your car insurance, therefore you need to pay it, which will decrease your bank account. And that's kind of the way it works for the electrons, because everything that you are trading is negative. It is sort of backwards from the way that you might think these things should work. So let's pick on mixing some magnesium with some oxygen. This is a little combination reaction. If I burn magnesium in the presence of air, which has oxygen, I will get magnesium oxide as a product. So in order to kind of get a grip on the reaction part, we got to back up a little bit and look at oxidation numbers. We did related things in many ways when we pass through nomenclature. So we're going to take a lot of those same rules and kind of just rehash them, and then expand them a little bit to provide explanations for things that, when we went through the nomenclature, I said, just pretend it's true. Okay, such as why, when you put two non-metals together, we make the assumption that one of them is positive. So that begins to get explained better via the ideas of redox. So oxidation numbers, we'll call them implied charges. So we start with the idea that if you have a pure element, it's all by its lonesome, nothing else stuck to it, it is considered to be zero in its oxidation number. You haven't gained any electrons, but you also haven't lost any electrons. So we look at a silver atom, it's 0. We look at a oxygen molecule because it's diatomic, still 0. I didn't gain or lose any electrons. Phosphorus, weirdly, can sometimes be found in nature as a 4-atom molecule, still 0 as far as oxidation numbers are concerned. All those things we assigned charges as we were passing through nomenclature. Whatever the charge was is the oxidation number. Okay, that's just kind of, like I said, a rehash of what we've already done to some degree. A sodium ion, so its oxidation number is +1. Calcium ion, oxidation number of +2. Oxide ion, oxidation number of -2. Now, oxygen and hydrogen get their own rules, which have each an exception. So oxygen in a molecule, okay, so like with another atom of something different, pretty much always is -2. There's an exception, and we did see this just a little bit, and I just said, just assume it's true, which was peroxides. We saw them a little bit when we were talking about polyatomics in nomenclature. This is one of the rare cases when your oxygens are assumed to be -1. You have to have an element from group 1, an alkali metal, at the beginning of your molecule in order to actually make this work. And I picked on the most common one there, hydrogen peroxide. Hydrogen also has kind of its own rule. We almost always see it as a +1. It's the beginning of a bunch of acids. It's part of things like bicarbonate, hydrogen carbonate. It's part of some other molecules. If you happen to stick it to a metal, rare but does occasionally happen, not only is it written at the end of the molecule, because it is stuck to a metal, it is called a hydride, and we assume its oxidation number is -1. Now, fluorine, when it's with friends, is given the oxidation number of -1. If we take any binary compound, so 2 different elements, whichever one is closest to fluorine is assumed to be the -1. So let's look at my picture here. Electronegativity is something that we will circle back to again in a later chapter. So it gets introduced a bit here. You will see that they're sort of color-coded. A huge number of the metals have relatively low electronegativity, hydrogen being an exception. If you look at the number value written below the hydrogen, 2.1, it actually fits from the way the table is organized between boron and carbon. So hydrogen doesn't quite follow the rules. There's also some heavy metals down later in the table that don't follow the rules quite as well. But look at the red square, okay? In the world of electronegativity, Fluorine is king, okay? It is the electron pig because it likes to hang on to its electrons kind of tighter than anybody else, which is why things that are closer to fluorine, nitrogen, oxygen, chlorine, bromine, behave a little bit more like the fluorine than they do like the other nonmetals. So one of the things we also said in nomenclature was make your molecule charges add up to 0, okay? So this works as long as you actually have a neutral molecule. We occasionally see things that are not neutral molecules. Specifically, this usually applies to polyatomics, which is the last rule. If you are making a compound that's actually not totally neutral, then all of your oxidation numbers must add up to the charge. So let me give you some examples. So what if you had a single atom of phosphorus instead of P4? Still 0. How about hydrogen as a diatomic metal? Okay, a diatomic molecule, actually, I should probably call it. No other elements were involved, so it has an oxidation number of 0. CO, not cobalt, okay, carbon monoxide. We're gonna kind of start on the right-hand end, almost like we did when we were calculating the charges for the transition metals. So we assume that oxygen is behaving normally and has a -2. But then that also means that since this is a neutral molecule, my carbon must be +2. So this begins to kind of weave two rules together. One is oxygen is closer to fluorine than carbon is, so it's the one that's negative. Carbon is behaving as if it were positive, and it is giving you what you would not expect as a normal charge on carbon. We're digging deeper and deeper into the why this happens, and a lot of it is based upon electronegativity. How about hydroiodic acid, HI? Well, it's two nonmetals, but hydrogen's normal. It's a +1. The iodine's a -1. How about sulfur trioxide? Note, there is no charge. It is not a sulfite, because if it was a sulfite, it would have a -2 like the molecule below it. We need to make everything match up. You have 3 oxygens. They are each -2. So there are 6 negatives in this molecule. In order to make everything match up, my sulfur needs to be +6. And actually, +6 is a somewhat common oxidation number for sulfur. Now we hit a polyatomic. Sulfate, SO4 -2. I want to have 2 negatives left over that do not get canceled out. So back to the oxygen idea. -2, I've got 4 of them. So that's 8 negatives. I want to have 2 left over. So my sulfur is going to actually be the same oxidation number as the one above. It's going to be +6 because I want 2 of those negatives to not get canceled out. How about N2O5? I've got 5 oxygens, so 10 negatives, but I've got more than 1 nitrogen. Take your 10 positives that you need and divide it in half, which means each of the 2 nitrogens ends up being worth +5. My phosphorus trifluoride. Fluorines are negative, -1. I've got 3 of them. In this case, my fluorines are -1, but my phosphorus is +3. It is not fluorine, and it is a couple of chunks away from fluorine, so it has to be the positive one. All right, so these are all the rules for the molecules in terms of oxidation numbers. Now we need to start applying those rules for the reactions. You will often, not always, see that when you make a metal and a non-metal react, a fair chunk of the time, the metal is the one that gets oxidized and the non-metal is the one that gets reduced. All right, so look at your molecule or your reaction here. We've got 2 coppers, an oxygen, and 2 copper oxides. I'm going to flip over to the whiteboard so I can show you a little bit more detail in terms of what I'm doing in my labeling. So there's my I forgot my coefficient. There's a big 2 out there. All right, so here's my reaction. So I'm going to go through and I'm going to put an oxidation number. Pick one, either put them on top or put them on the bottom, okay? Whichever one seems to make the most sense. I'm going to do it on the bottom. So my copper, because it's pure, has an oxidation number of 0. And I'm going to put a little hash mark through it so it actually looks like a 0. My oxygen molecule has oxidation numbers of 0. My oxygen on the right-hand side, because it's inside a molecule and it's not a weird thing like a peroxide, is -2. And that makes my coppers +2. And then I'm going to connect them. I'm going to connect my copper, and I'm going to connect my oxygen. And I'm going to read them in the direction of the arrow. So since my copper went from 0 to +2, and that is an up, okay, think number lines, okay, this is the thing that got oxidized. My oxygen started out as 0, and now it's in the hole, okay? It went down 2 steps, so it is the one that got reduced, okay? If your oxidation numbers go up when you read from left to right, they are oxidized. If they go down, they are reduced. So let's go through a few more examples. And then I just kind of wrote it out phrase-wise here. I wish I had more ability to kind of draw on my notes. That's sort of frustrated because I like to be able to draw the arrows. So how about if we look at 2 non-metals? nitrogen and hydrogen. So think about, again, what your oxidation numbers are. Your nitrogen, your N2, is a 0. Your hydrogen is also a 0. Okay, ammonia, NH3, is one of the only molecules in general chemistry that's written backwards. Okay, it's partly because ammonia is something that people have sort of been aware of and utilized from a sort of chemistry point of view for centuries now. So the negative in that molecule is actually the N. Okay, that's the beginning. And then their hydrogens are normal. Okay, your hydrogens are +1s. So if we read in the direction of the arrow, my nitrogen started out life as 0 and went down to a -3. So it is reduced. My hydrogen started out at 0, but it went up to +1. So it is oxidized. One of the things you should be beginning to grasp here is everything is paired. You cannot have a reaction that has just reduction without any oxidation, because your electrons had to go somewhere. You have to have a minimum of one of each. One thing reduced and one thing oxidized. Now, sometimes you might have more than one of each, but bare minimum, you got to have one oxidized and one reduced. Remember all those spectators from precipitation? We're going to see something kind of similar for some redox. Let me switch back over to my whiteboard again. All right, so we are looking at magnesium and 2 silver nitrates and we flop some stuff around. This is also sometimes known as a single displacement reaction. One thing is trading partners as opposed to precipitation style reactions where 2 things are trading partners. All right, let's go through and do all of our numbering for our oxidation states. So 0, because magnesium is by its lonesome. My silver, because it's in a molecule, is +1. And look at your nitrate, okay? It's nitrate is nitrate on both sides. You could just write -1. You could go through and calculate the nitrogens and the oxygens separately, but it won't actually change your answer. So -1 in that. My magnesium is +2. And then this silver is 0. So again, I'm going to kind of look left to right here. My magnesium went from 0 up to +2. So it's my oxidized one. My silver went down. It started out life as +1 and it went down to 0. So it is your reduced one. Nothing happened in terms of trading electrons to my nitrate. And although textbooks do not call it a spectator when you are talking about redox reactions, that is actually essentially what it is. It is hanging out in the beaker, swimming around, doing nothing. Okay. It is watching. It is not being oxidized and it is not being reduced. And this sometimes happens, especially in reactions where you have two metals. So +1 up to 0, or +1 down to 0, reduced. 0 up to +2, oxidized. All right, 2 more terms. So since there actually might be concerts this summer, if you want to go to a concert down at the amphitheater and you buy a ticket, I don't even know who's playing down there this summer. There's like 6 or 8 concerts that are actually happening that are already scheduled. But if you are going to a concert there and you get on, say, Live Nation or Ticketmaster, or there's a couple of other websites that tend to be clearinghouses for selling concert tickets, they are ticketing agents. They are selling tickets for the band that you are going to see. They are not the people who are going to be on stage playing. So an oxidizing agent oxidizes something else, but it gets reduced. A reducing agent then, because these are also paired, a reducing agent will get oxidized and it will reduce something else. So the agent is what they do to another element. So if I pick on potassium and chlorine, all right, so I got metal, non-metal. My potassium is 0, my chlorine is 0. Over on the other side, I'm going to see if I can push these a little bit more sideways so that they're underneath the K and the Cl. My K, my potassium is +1, my chloride is -1. So my potassium is the one that's getting oxidized because it's going up to +1 because it started out life as 0. My chlorine is being reduced. And so what that does is that makes my, I actually realized I meant to put more words in here. So this makes, since the potassium is oxidized, okay, so potassium is the reducing agent. And, supposed to be an and chlorine is the oxidizing agent. All right, doing laundry, okay? If you want your socks to be white, maybe you use Clorox, which has sodium hypochlorite in it. The hypochlorite is an oxidizing agent. It steals electrons of the pigments that color the dirt from your clothing. If you want to improve the color of something without bleaching it, okay, without turning it white, there are a number of other things on the market like OxyClean, which has a much less powerful oxidizing agent. Therefore, it won't accidentally turn your pink shirt white. Okay, so there's reasons why some of these things work the way they do, and it's all about the chemistry. Let me give you a couple more examples for oxidation numbers here, a couple more complicated ones. How about PF6? This one has a minus charge, meaning that everything has to have, or when I'm total up my sum, I have to have one negative left over. If I make all my fluorines -1s and my phosphorus a +5, one of those negatives from the 6 fluorines doesn't get canceled out. How about H2ASO4 minus? And I actually realize I have a plus where that's supposed to be an equals. This is supposed to be an equal sign. So this one I kind of did from the outside edges toward the middle. I assume hydrogen is normal. I assume oxygen is normal. So I've got 2 hydrogens and 4 oxygens. So 2 positives and 8 negatives. I want one of those negatives to not get canceled out. And actually, I really hosed that one. I have a typo. That's supposed to say +5. Because +1 and +1 and +5 make 7 positives. To go with your 8 negatives, yeah, I really screwed that one up. Because I'm used to doing these on the board. And didn't correct my notes. And then I'm going to do one more, and then we're going to take a break, and then I'll come back and do the weird one. So UO +2. So uranium. Okay. Uranium. And I actually realized okay, this is supposed to be a uranyl, okay, one of the rare polyatomics. And I realized I also have something missing. Out of this one. This is supposed to have 2 oxygens in it. Let me go see if I can fix this. That. It's supposed to be UO2 +2 in order to have the uranium be 6 positives. Because that way I have 4 negatives and 6 positives gives me 2 positives left over. Yeah. When I type this out from some previous notes, I definitely kind of screw that up a little bit. All right, so let's take about a 10-minute break, and I will come back and talk about the complicated example that's the next line there.